Okay, guys, welcome. Today we're going to talk about finding the complete solution set for linear Diophantine equations. Now, before we do that, we're going to need some theorems first. Okay, so the first theorem says that for integers a and b, we know that the GCD of a and b is 1, or in other words, a and b are relatively prime, if and only if there are integers m and n, such that am plus an is equal to 1. Now, again, we have an if and only if statement, so if we want to prove it, we have to show it in both directions. Now, the forward direction, if we assume that the GCD of a and b is equal to 1, then we know that this is solvable by our extended Euclidean algorithm, right? Because if the GCD of a and b is 1, then the GCD of AB, of course, divides 1, since that's over here. So we know that that's solvable. Now, in the backward direction, if we assume that AM plus BN is equal to 1, then we know that the GCD of A and B would have to divide 1, right? Now, if the GCD of AB divides 1, that forces, we don't have a choice, the GCD must be 1, right? And that completes the proof. Okay, now the next theorem that we'll need is that if the GCD of two numbers D and A is 1, and we know that D divides A times B, then D has to divide B, right? Or in other words, if D and A are relatively prime and D divides the product AB, then we know that D has to divide B. So the proof works like this. So we know that the GCD of D A is 1, then we know by the previous theorem that there exists M and N such that DM plus AN is equal to 1. Now, if we multiply both sides by B, we get this equation here, right? So just distribute a B on the left side, and then 1 times B is B. Now, since D divides A times B, we know that D times some integer K is equal to AB. So we're going to plug that in, right? So this AB right here is going to become DK here. But now we can factor out a D on this side, and we get D times BM plus KN. And since this is some integer, we've shown that D times some integer gives us B, which tells us that D divides B. All right, and that completes that proof. Okay, so let's look at the following example. So we have 34x plus 40y is equal to 2. Now, if we wanted to solve this for slope-intercept form for a second, and we allow for coefficients to be rational numbers, then we get that y is equal to 2 over 40 minus 34 over 40 times x, right? And we see that the slope is equal to negative 34 over 40, right? And we'll reduce that in a second, but I want to show something here. Now, earlier we found that a particular solution for this in a previous video, we found that x is equal to negative 7, y is equal to 6 will work, right? So if you were to put this in point slope form, now that you know that a particular point on this line, once you plug it in, you would eventually get this equation here, where we have the y coordinate here and your x coordinate here, well, the opposite of your x coordinate here. Now, if we want only integer solutions for x and y, we need to force x to be 40 times some integer k minus 7, right? Because if we have that, if we plug that in, the 7 and the negative 7 will cancel. And then in the next step, the 40s will cancel. And we'll get that y is equal to 6 minus 34k. And both of these would be integers. Okay. Now, since we didn't reduce 34 over 40, we missed some solutions. So I want to highlight the fact that it's important that you reduce these equations. Now, if you reduce 34 over 40, you get that the slope is now 17 over 20, or negative 17 over 20, I should be saying. Now, since the GCD of 17 and 20 is 1, or in other words, they're relatively prime, and we want 20 to divide 17 times x plus 7, we have that our previous theorem will tell us that 20 must divide x plus 7, right? So in other words, in order for this to happen, we need x to be 20k minus 7, where k is an integer, so that the 7s cancel out and we get 20 divides 20 times something else, which of course makes sense. So now once we plug in this 20k minus 7, our 7s again cancel out and our 20s cancel out, and we get 6 minus 17k. And that's our complete solution set for our Diophantine equation. So you can pick any integer any integer k, and that will generate integers for your x and y. All right, so let's go ahead and we'll do an example. Let's find the complete solution set for 4x plus 3y is equal to 1. Okay, so we want to solve for slope-intercept form, which means getting y by itself. So if we do that, we get 3, 1 is equal to 1 minus 4x. And if we divide by 3, we get the y is equal to 1 over 3 minus 4 over 3x. Okay, now if we go back, what do we want to do at this point? Well, we want to have integer solutions, and we have a little bit of a problem here because we have that this is now also not an integer, right? So we have to be a little bit careful here. Now, if we want this to be an integer, we need x to be a number plus a third or something like that, right? So what we need, so actually now I'm realizing that this was copied wrong. This should be 4x plus 3y is equal to 3, which is going to help make this a little bit easier, right? So now if we do that, that's going to make this now a 3, which would now make this when we divide by 3, 1. So that's going to make our problem a little bit easier. Now we know that one solution is when x is equal to 1 and y is equal to -1 would get us this equal to 1. So since I want it to be equal to 3, trying to squeeze that in there without it looking too bad. Anyway, our solution is going to be 3 and y is equal to -3, because then we would get 12 minus 9, which would indeed give us 3. So now if we incorporate this and put it into point slope form, we're going to get y is equal to a positive 3 once we move it over, plus 1, and then minus a 4 over 3 x minus 3. All right, so we get y is equal to 4 minus 4 over 3 x minus 3. So now since our slope is reduced, if we make x equal to 4 times an integer k, 3 times an integer k, and then plus 3, right? When I plug it in, that will cancel out the 3 and then also cancel out the 3 that's being divided, which would give me that y is equal to 4 minus 4 over 3 times x, which is 3k plus 3 minus 3. So our 3's cancel here. The 3's also cancel here, and we get that y is equal to 4 minus 4k. All right, so those are our two solutions for x and y, and that would give us the complete solution set for this Diophantine equation. All right, so that concludes this video on obtaining the complete solution set of a Diophantine equation. I hope you enjoyed, and I'll see you next time.